Hi everyone, I'm going to introduce our paper, Sharing Parameter by Conjugation for Knowledge Graph Embeddings in Complex Space. A knowledge graph is a directed graphical representation of entities and relations in the real world. It can also be described as a semantic network, abstracted entities and relations, visualized database. A triple, for example, animals, is, living things, is widely used as a representation of elements in the KG. Animals, is, living things are the head entity, relation, and tail entity, respectively. KGs can be applied in diverse natural language processing tasks where knowledge is required. Information retrieval, entities recommendation, relation discovery, and so on. For example, Google's KG can help answer users' next questions before they ask. Knowledge graph embedding models are designed for automatic link prediction. Translation approaches, including Trans-E and its variants, describe embeddings using real number representation. Although these simple models cost fewer parameters, they can only encode 2 or 3 relation patterns. For example, Trans-E cannot encode symmetric relations. Complex, it creates embedding with complex number representation, which can handle a wider variety of relations than existing approaches using only real numbers, among them symmetric and anti-symmetric relations. 5-E utilizes Mobius transformation, a projective geometric function that supports multiple simultaneous transformations in complex number representation and can embed entities in much lower ranks. The theoretical space complexity of KGU models are often O and E, dE plus NR, dR, which is proportional to the number of KG elements, that is, entities NE and relations NR, and embedding dimension dE, dR, respectively. Scaling a KG is problematic as NE and R can go up to millions. Also because KGE models are often shallow machine learning models composed of simple operations. For example, matrix multiplication. Caution that a shallow model needs a large dimension size D to depict the data feature, yielding the issue of the drastic increase of embedding parameters. KGE models represented using complex numbers have state-of-art performance, while they demand high memory costs. For example, if using one of the best models complex to create embedding for the benchmark dataset FB15K, whose NE of about 15,000 and NR about 1,000, and the best performing dimensionalities dE of 4,000, dR of 4,000, will result in the parameter size of around 65 million, considering the data type 64-bit integer who has a size of 8 bytes in PyTorch. The memory cost will be around 500 megabytes. A KG for real-world application could have a much larger size. For example, KG of IBM contains entities more than 100 million and relations more than 5 billion, which is actively in use and continually growing, will need 150 terabytes memory to do link prediction task. To mitigate the computational load, we propose a parameter sharing method, that is, using conjugate parameters for complex numbers employed in KGE models. Our method improves memory efficiency by 2 times in relation embedding while achieving comparable performance to the state-of-art non-conjugate models with faster or at least comparable training time. We demonstrated the generalizability of our method on 2 best-performing KGE models, 5-E and complex, on 5 benchmark datasets. Here is the method formulation. Let A1, A2 denotes the relation embedding matrix. Our method constrains half of the parameter A2 using the complex conjugate of the other half A1 bar, that is A2 equals A1 bar. It is model dependent to specify which parameters are suitable for conjugation. By using our method, the original model complex is adapted to the parameter sharing model complex epsilon. Our method transformed the original model 5 E into the parameter sharing model 5 epsilon. In this model, parameters play distinct roles at different positions, and the Basel conjugation position are the principal and secondary diagonal positions. Note that experiments show that the negative conjugation method, which uses half of the negative conjugation, achieves similar performance. Although the negative conjugation on this model is equivalent to restricting the original Mobius function to the unitary Mobius transformation, our approach is much more general to a variety of representations. FB15K is a subset of freebase, the contents of which are general facts. WN18 is a subset of WordNet, a database that features lexical relations between words. Yago 3 to 10 is the largest common dataset. It mostly describes attributes of persons and contains entities associated with at least 10 different relations. FB15K to 237 and W18RR are subsets of FB15K and WN18, respectively, where inverse relations are removed to prevent test leakage. We adopted all of the 5 datasets for comprehensive comparison of models and followed the standard evaluation protocol for KGE models using MRR and hit-at-end metrics. We experimented using different hyperparameter settings to explore how hyperparameters influence our method. To do this, we used the Basel hyperparameter settings for the original models, marked as nebula or no mark, and experimented on the same settings using our conjugate models and the ablation models. We also fine-tuned the Basel hyperparameter settings for one of our conjugate model, 5 epsilon, noted as diamond suit, to see if it can perform better. The main experimental results are shown in the following tables. The numbers with bold face indicate the best result among all the numbers. The results show that both complex epsilon and 5 epsilon achieves results comparable to their original models on the dataset without test set leakage, and obtain the same optimal accuracies on all datasets with possibly required fine-tuning. In addition, the training time of 5 epsilon is significantly reduced by 31%. These tables show comparisons of datasets with or without text leakage issue. On datasets which have text leakage issue, accuracy fluctuations will be different, but the fluctuations can be easily solved by hyperparameter tuning. The ablation studies results are shown in these tables. We did 2 kinds of ablation studies. We know the reducer calculation is mainly in the regularization process because we only have half of the parameters. Thus, we experimented where the regularization term is only half of the parameters on the original model. See results for 5 ER to explore whether the performance fluctuation using our method is similar to the effect of reduced parameter regularization. Then we experimented with conjugations in different positions to explore how the models perform differently. We set negative conjugation in model 5 epsilon n and a vertical conjugation in model 5 epsilon v, where parameters are the conjugation of parameters in their vertical direction instead of the diagonal direction. In model 5 epsilon h, which is the horizontal conjugation, parameters are the conjugation in the horizontal direction. The studies show that, first, only reducing parameters in the regularization process will hurt the accuracy significantly, which indicates the conjugation method reserves the model's ability better than simply reduce parameters. Second, the negative conjugation model performs as well as the positive method. Last but not least, conjugate method should choose suitable positions. For example, 5 star epsilon v and 5 star epsilon h do not perform as well. In conclusion, we propose using shared conjugate parameters for transformations. Our method suffices to accurately represent the structure of the Kg in the complex number represented KGE models. Our method can help scaling up Kg with less carbon footprint easily. First, it reduces parameter size and consumes less and at least comparable training time while achieving consistent accuracy as the original model, including reaching state-of-art results. Second, it is easily generalizable across various complex number represented KGE models. For future work, we would like to deal with the interpretation of the linear constraint of our method. For example, to explore the effect of this method on different relation patterns.